going to give you a quick review for previous class. We talk about the diffusion mechanism. In these lectures, we are going to show you how to obtain the diffusivity of materials and what's the relationship between the diffusivity and the atomic jumping process in crystals. So the outline can be divided into two parts. The first part is the thermally activated diffusion. That means the atomic jumping process is rely on the thermal energy only. And this process can classify as the random walk or correlated atomic jumping process. The random walk means this atomic jumping process is nothing related to previous jump or next jump. And the correlated atomic jumping process means this jump actually is correlated with previous jump or next jump. This kind of jumping process, we call it is a correlated atomic jumping process. So how to obtain the diffusivity? What's the relationship between the jumping process belongs to the random walk or correlated jumping process? What's the relationship between diffusivity and this kind of atomic jumping process? And in the second section, we are going to talk about the diffusion in crystal structures or crystal lattice. And first of all, we are going to introduce several diffusion mechanisms in crystals. And this part, we put more efforts on metals. And the second part, we talk about the atomic diffusion in ionic solids. What's the difference between the diffusions in metals and in ionic solids? In ionic solid, we need to pay attention about the charge balance, the concept, especially for the charge balance during diffusion process. So as we know, the atoms, as long as these atoms have higher energy, which can overcome the energy barrier, so that this from a thermal energy, then this atom is going to make a successful jump from location 1 to location 2, right? So this is we call it as a thermally activated jump. And based on the classical mechanics or quantum mechanics, you can estimate the atomic jump rate expressed like atomic vibration frequency times the probability of crossing the barrier, right? So the simulation based on the quantum mechanics part is it tells us that the atomic jump rate in specific direction gamma prime will be equals to atomic vibration frequency, which you derive from harmonic oscillation models and the exponential, the probability term. So based on this, we know the atomic jump rate is associated with bond strength, reduced mass, and energy barrier of these materials. And energy barrier, this is migration energy barrier, right? And the working temperature, right? Okay, so now we have some idea about what's the atomic jump rate. And as you know, atomic jump rate actually is the what we observe in our crystal, right? Diffusion phenomena, actually you can explain that it is what you can observe that in your experiments is something can describe like the diffusion phenomena in macro scale. But atomic jump rate actually is, you describe this diffusion phenomena in micro scale. So this is the atomic jump rate. We try to correlate the diffusion and atomic jumping process. So we use the capital R this is a vector. So what's a capital R? That means after time tau, after diffusion, or after time tau, and the atoms, your interesting atoms, diffuse from here to here, and the total displacement, you call it as a capital R, and each jump we use as a small r to represent it. So the capital R is a summation, sum of the small r, sum of each jumps, right? R1, R2, R3, and so on until to N tau. And N tau is the total numbers of jump. So what's the N tau is? The gamma is the total jump rate times the time period, diffusion time period tau. So you got the total numbers of jumps. So the capital R is small r plus R1, R2, R3 to N tau, because this atom already made the N tau times jump. Okay, so we try to correlate the diffusion with the atomic jumping process. So as we know, if you directly average the capital R, and due to the capital R is a vector, and always, and if the case we're talking about is a random walk, so you average the capital R, and the results would be equals to 0. So the average displacement is not a good indicator to describe the diffusion phenomena which you observe in macro scale. And here, how about the mean square displacement, which is you use the capital R to dot capital R and take the average on it. So then you will get a scalar. So following, we just try to show that mean square displacement can well describe the diffusion phenomena. So have a look here. Finally, we can get the quantitative description for mean square displacement R, capital R, can be expressed like the N tau is the numbers of total jump times the mean square jump distance, and plus the second term, which is a sum of the cosine theta between the I and I plus j times jump. And as you know, what's the N tau is the diffusion time period is correlated with that, right? As long as you prolong the diffusion time, then you got the larger number of N tau, and small r actually is correlated with the crystal structure. So it turns out the capital R, mean square displacement, can well describe the diffusion phenomenon, but in random walk. As you know, random walk use sum of the cosine theta term. This term will becomes to 0. So next slide is based on this assumption. It is the random walk. So we try to show you how to calculate the mean square displacement based on what. In what kind of cases is the diffusion from a point source. So before diffusion, we got a point source at the center of this ball. Then after diffusion for time tau, then we can observe the particle distribution like this, and the total number of particles we call is NC. So what's the mean square displacement? Actually is your sum of the capital R squared times the numbers times each the numbers of particle at specific R, capital R squared, and you sum them up. Then you divide it by the total numbers of particle NC. Then you can get the mean square displacement. So it's easy to get that, right? The total numbers of particle can be expressed like a concentration profile times the share of the share, and you 4 pi r squared dr. and you integral from 0 to infinity, then you got the total number of particles. And the upper portion would be what? The R, what you need to do is the R probably the R1 square, then you times the numbers of particles at R1, within R1, or far away from the initial point of source at R1, then you plus, then you got the R2 square times the numbers of atoms which is located from the initial point with R2. So it's the R2 square times the numbers of atoms located at R, and R you assume it you integral from 0 to infinity, then you can get this. After calculate, you can get the mean square displacement. But this case actually is a three-dimensional diffusion cases, so we can simply get the concentration profile as radius and tau, right? So that's what we learned in lecture 3. You can simply get this concentration profile, and this is three-dimensional cases, so it's a 3/2 here. We substitute the concentration profile with this one, then you can get the mean square displacement is 60 tau. And as we mentioned, this mean square displacement is proportional with diffusivity and tau. In the diffusion, this case, is diffusion from a point source, right? And if as we know, if the diffusion, it is not a three-dimensional diffusion case, it is one-dimensional. For example, like the point source diffuse into one-dimensional narrow wire, then you need to modify the concentration profile with this one, and this term should be modified as, because it's a narrow wire one-dimensional, should be dr. dr is a length. You integral the total length of this narrow wire, then you can get 2d tau. And 2D case, then you just modify the concentration profile by this results, and you need to integrate the area. So area will be 2 pi r dr. Then you got the result is 4d tau. So depending on different dimensional of diffusion sources, so you need to substitute different concentration profile and also the second term here. Then you can get a different results here. So one-dimensional is 2d tau, two-dimensional is 4d tau, and three-dimensional is 60 tau. And this is we successfully get the mean square displacement expressed like 60 tau in this case, and based on the concentration point of view. But we also can get the mean square displacement based on the radial probability point of view, right? So after so as long as we get the radial probability as a function of r and tau, then you substitute this term, then you also can get mean square displacement. So in our textbook, it tells us to use the one-dimensional cases to get the radial probability, although it is not as correct as you expected, because in this case, actually we use a three-dimensional case, but however, converted to probability part, we use the one-dimensional cases to get the radial probability, but it is very complicated in three-dimensional cases to get the radial probability. So that's why in our textbook it only introduced the one-dimensional method to get the radial probability. Is too complicated. So based on these results, we can get the probability expressed like this. Then as long as you know the probability, you substitute this result here, then you got the mean square displacement is equals to n tau. It's total numbers of jumps of the diffusing atoms, and the mean square jump distance And the n tau can be expressed as gamma, atomic jump rate, times the diffusion time period tau. So this is the same. So we got the diffusivity of the material, which describe how fast the diffusing atoms moves in your materials is proportion to the atomic jump rate. This is the total jump rate. This is gamma. It's not a gamma prime. Gamma prime is the atomic jump rate in specific directions, and this is the total atomic jump rate. So you need to consider all possible jumping directions. And this is the mean square jump distance. Small r actually is the distance of each jump. Okay, so now we successfully link the diffusivity, which you observe in macro scale, with the material property, atomic material property included the beta, bond strength, reduced mass, energy barrier, and temperature, and also the crystal structure, right? So the right-handed term included the gamma, atomic jump rate, and mean square jump distance is especially the mean square jump distance is highly associated or related with atomic jumping behavior, because that will be related to the atomic diffusion mechanism and crystal structure, right? Some people probably will ask why. Because r small r is the jump distance, the jump distance. Jump distance depending on the crystal structure, right? Because this jump distance is the atoms must jump to the nearest possible available locations. So nearest one, so this one in crystal must associate with the lattice constant, so will be related with the crystal structure. And also jump distance were related with the diffusion mechanism, because different diffusion mechanism diffusion mechanisms actually have different diffusion paths. For example, like the interstitial diffusion mechanism means the atoms moves from interstitial size, right? And for vacancy mediated mechanism, that means the atoms exchange with the vacancy at substitutional site, right? So will be depending on different what kind of diffusion mechanism we talk about. Okay, so make a quick summary. In the first part, we use the quantum mechanics to tell you how to estimate the atomic jump rate. Gamma prime expressed this term would be the atomic vibration frequency times the probability of crossing the barrier. And this will be related to with the crystal structure and atoms, what kind of atoms we're talking about, and also the temperature, working temperature, and the energy barrier or migration barrier of these materials or this crystal. And second part, we use the random walk process as an example and try to find a good indicator to link the diffusion phenomenon or diffusivity with atomic jumping process. So based on the random walk, which the example here we talk about is the spreading of the point source. Then you got the mean square displacement equals to 60 tau, and based on the radial probability point of view, you got the mean square displacement equals to gamma tau, and mean square jump distance will becomes equal. So you got the diffusivity equals to total jump rate times the mean square jump distance divided by 6. But actually, the results we got here, we make a very important assumption to simplify the case we just talked about or discussed is a random walk process. So because we assume it is random walk, so based on the definition or the equation we derive for the mean square displacement is like this, right? Because if it is random walk, so the second term will becomes to 0. So the mean square displacement can equals to n tau times the mean square jump distance. But that is the cases we talk about is a random walk or non-correlated jumps, right? But however, if the diffusion is through or with correlated jumps, that means the sum of this cosine term will not 0, so it's a non-zero term. So here we need to modify. We need to modify the diffusivity we derived, right? So how to modify that? Before that, we need to define a factor. We call it a correlation factor, because this factor is define the correlation between each jumps. So the correlation factor is defined as f, and you just directly divided this equation by n tau mean square jump distance. So you use a mean square displacement divided by n tau mean square jump distance equals to 1 plus this term divided by this term. So based on this, based on the first terms, you got the mean square displacement can be expressed like n tau mean square jump distance times what? Times f. We got the f here. If you check the previous results, actually, this is n tau times mean square jump distance. Based on the radial probability term, actually, we just, if it is non-correlated jumps, we need to end it the f here. And so there are 3 cases to give you more information about the correlation factor f. So if f equals to 1, so at what kind of situation f will be equals to 1, and this term will becomes to 0. So this is the case we just talked about is non-correlated jumps, because sum of the cosine term becomes to 0. That means this the jumps is random walk, or we call it non-correlated jumps. And the other extreme cases will be when f equals to n tau. So f equals n tau, what's this mean? F equals to n tau tell you the mean square jump distance, or mean square displacement, this one equals to what? N tau square mean square jump distance, right? So it's something like this. It's n tau times r dot n tau times r. So you got the n tau square mean square jump distance. So if you substitute this term into here, then you will get f equals to n tau. So what this means is, that means the cosine equals to 0. That means each jumps are, the jumping directions are the same direction, are identical. For example, the atoms always jump to the right-handed side, so the cosine theta becomes to 0. So you can get this mean square jump distance, then f equals to n tau. But it is not really happens in your materials, right? Okay, but this is extremely case. And the other extreme case is the f equals to 0. So at what kind of situation f will becomes 0? That means mean square displacement is 0. So that means this jump is to right-handed side. Next jump will be the opposite direction, will be go to left-handed side. So go right, go left, go right, and go left. So that will result the mean square displacement becomes to 0. Okay, so here we know in order to get more universal equations related to diffusivity, so we modify the this one actually we derive from radial probability. We ended F to allow this results can be used to most of cases. So we modify F correlation factor here, and the rest of part actually is the same as previous line. So in this case, you can have idea like diffusivity can be expressed like the gamma total atomic jump rate mean square jump distance divided by 6 times the correlation factor F. And don't forget the total jump rate, you need to consider what? How many atomic jump rate in specific directions, and you times the possible jump distance, Z, then you becomes the total atomic jump rate. Then F is a correlation factor. So don't forget, if F equals to 1, the diffusivity is that means a random walk, right? And what kind of situation is the random, the F will be equals to 1? For example, like if the diffusion process is interstitial diffusion, the atoms can move through interstitial size. No limitations for interstitial diffusing atoms because the diffusing atom can move anywhere, any interstitial size. So F equals to 1. For the vacancy, the same, right? Vacancy can move to any. If we have a vacancy at substitutional site or lattice point, then the vacancy also can move to anywhere. No any limitations for vacancy too, right? But let's a vacancy mediated diffusion. What's a vacancy mediated diffusion? That means the diffusing atoms at substitutional site, it need to exchange the size with surrounding vacancy. So based on these cases, the atoms need to, first of all, let's must surrounding vacancy nearby these diffusing atoms. Then that will allow these atoms to jump in or exchange the site with that vacancy, right? So this kind of situation, you know, there's some limitation for these diffusing atoms. So the F will not becomes or smaller than 1, but larger than 0. So usually in most of cases, the correlation factor is between 0 to 1. If it is random walk, definitely is 1. But if it is not, you need to know the value for F. Otherwise, it's very difficult to get the diffusivity of your material, right? So next slide is going to show you how to estimate the vacancy mediated diffusion process. How to estimate the correlation factor for vacancy mediated atomic diffusion. And in our textbook, it provided you 2 methods. The first one we call is a very rough estimation for F correlation factor. You can before we move here, then you can think about that. F equals to 1, you can think it is a random walk. You can consider as a 100%. And 0 is what? Is the diffusivity. 0, the diffusing atoms just stayed. And just the diffusion doesn't help happen, right? But because the diffusing atoms went back to its original site. So it's F is low, definitely is between 0 to 1. So the idea is that how to get the F? We can just use the 1 to minus the useless. We can use the 1 to minus the useless jumps, which is not have no contribution to the diffusion process. Then we can get the F. The concept will be that. So in this case, in the beginning, the atom is at here, and the vacancy will be here. So next jump will be the atoms exchange the location or site with vacancy. So we become here. So the probability, and next will be like this, right? The vacancy will becomes the right-handed side, and atoms becomes to left-handed side. Then after like a certain time period, the vacancy probably is moved to other exchange with other atoms and move to somewhere. But after certain time period, there are other vacancies move to this location. Then if the atoms exchange back and move back to this location, then that means this jump and this jump is nothing, have no contribution to the diffusion process. So we just use the 1 to minus these two useless jumps. So be 1 minus 2 over z. What's a z? Z is a correlation number. So means the atoms only the probability to allow A to exchange with V actually is 1 over Z. So this change with jumps to vacancy. This is 1 over Z. So I minus this term and also this term. Then we can roughly estimate the correlation factor. Just use 1 to minus the 2 out of Z jumps, which is no contribution to the tracker diffusions. Then you can gather the correlation factor F. But the other method to estimate the F is based on the definition of correlation factor F. Based on the previous slide, you know this is how we define the correlation factor F. So in order to get the F, you need to sum this cosine, the average of cosine theta term. And the detailed deviation, you can check the lecture note, page 15.1 to 15.5. So if you have a look here, sorry. Okay. So if you have a look here, you can find that this is what the definition, right? And if I want to sum the average of cosine theta, then after series deviation, you find that this average cosine theta term is related, can be expressed like this average of cosine theta term and to J. And after series deviation, you got the F can be expressed like this. And what's the average of cosine theta? How to get this one? So the very important would be the average of cosine theta of the angle between the successive jumps must be the same for all pairs of successive jumps. That means this result will be equals to what the average of the cosine theta between the successful jump will becomes to the same with you just directly average this cosine theta term. And this cosine theta actually can be get based on what? Based on the probability times the cosine theta. For example, the case is like we mentioned in our PPT cosine theta, the probability. For example, if these atoms jump to this location, for example, like the vacancy is in red, and this is blue is our atom, right? So the atom can jump into vacancy, and this probability is 1 over Z. And successive jumps means we jump here and backward and back to our original site. This is what we call a successive jumps. So this is the theta is 180 degrees C. So the cosine theta will be -1. So you got the average of cosine theta always is a probability times the cosine theta. This successful jump. The theta is the angle between these two successive jumps. And this the other term means that you can ignore the second order term. What does this mean? Some people probably will ask, yes, you make this jump and you backward and nothing. This is the average of cosine theta, and this jumps has no contribution to diffusion. And some people probably will ask, how about I jump here, jump this one, and jump back, and and it's also back to the original site, right? So we also can also can get the average of cosine theta. Yes, it is, but the probability for jump here, and jump back will be what? Will be very small, because will be 1 over, for this case this is FCC, so it's a 1 over z will be 1 over 12, and take the square. And also you got the numbers of this kind of jump. But this term actually is very small compared to 1 over 12. So most of people can just ignore the second order term. You just use the first order, the nearest vacancy or nearest atoms to estimate or write down the average of cosine theta. Okay, so let's back to. Okay, so the cosine theta actually is what we mentioned is you use the probability. Probability is 1 over z. If it is FCC is 1 over 12, and the cosine theta is the successive jumps. So you move layer and back to its original size, so it's -1. So you substitute this to here, then f is 0.85. But if you use this term to estimate, you will get the 0.83. So it's similar. The correlation factor is similar. No matter is you use this rough estimation or the based on the definition of correlation factor, you can finally get the F for vacancy mediated atomic diffusion. So here we just want to tell you that you need to the diffusivity. You got these results from the first and second sections, but consider to use this equation. For most of case, we need to put the f to modify it. And if it is random, we'll f equals to 1, and this result will be equals to with what we did derive in previous line. But if it is not it is a non-correlation, or it is the correlation jumps, then as long as we estimate the f, when we know the f, then we can get the diffusivity.